Hello, today I will present our project. Our main question is whether tabular learning can achieve generalization without using neural functional approximation, and we propose structured broadcasting Q-learning. Our motivation comes from compositional generalization. Humans can often understand new combination of familiar features. For example, after seeing a white cat and a black dog, we can still recognize the idea of a black cat. So we want to bring a similar intuition into reinforcement learning. In standard tabular learning, an update affects only the visited state action pair. Even if another state shares most of the same feature, each Q-value is stored independently. This becomes inefficient in vectored MDP, where the number of states grows exponentially with the number of features. To address this limitation, we propose structured broadcasting Q-learning. The key idea is simple. When one state action pair receives a TD update, we propagate part of the learning signal to structurally similar state. The goal is to improve early sample efficiency. This idea is inspired by kernel-based RL in continuous space. With kernels such as the RBF kernel, nearby states can share learning signals according to a distance metric. Our contribution is to adapt this idea to discrete state space. So we define a kernel estimator based on Hamming distance. The Hamming distance counts how many feature positions differ between two discrete states. And we convert this distance into a similarity weight using an exponential kernel. This weight determines how strongly the TD error is broadcast to neighboring states. This is a simple example. The two states differ in two feature positions, so their Hamming distance is 2. And we define a scalar TD error loss and take the gradient with respect to the kernel estimator. The resulting update has a simple interpretation. The TD error is not only applied to the visited state, but also distributed to similar states weighted by the Hamming distance. A key concern is that broadcasting may introduce biased update. To avoid this, the kernel estimator is used only as an auxiliary term. The combined value function is defined as the global Q value plus a weighted auxiliary Q value. The coefficient beta approaches 0 as the visit count increases. With this annealing scheme, SPQ preserves the convergence guarantee of tabular Q-learning. The algorithm has 3 main steps. First, we compute the TD error using the combined Q value. And second, we update the visited state action pair in the global Q table, as in the standard Q-learning. And third, we broadcast the same TD error to Hamming neighbor state through the auxiliary kernel estimator. And this is the overall architecture diagram of our SPQ implementation. And now we evaluate SPQ on diverse structured environment, including DNA promoter, light out, danger maze, forum grid, network routing, robotic arm, and standard benchmark environment like mini grid and taxi. And we compare these SPQ from the baseline Q-learning and DQN. This plot shows the learning curve across different environments, and the green curve corresponds to our SPQ. In several structured and sparse reward tasks, SPQ improves average reward in early learning phase. It meaning that SPQ reaches higher reward with fewer interaction. In the additional result, SPQ appears to maintain relatively stable in later phase performance. This supports our design goal, to gain early generalization from broadcasting while preserving the stability of tabular Q-learning in later phase. However, SPQ does not outperform the baseline in every setting. In the robotic arm task, where the state is discretized but the real distance, SPQ shows no clear advantage over the baseline. To conclude, we propose structured broadcasting Q-learning, which uses a Hamming distance kernel to broadcast TD error across structurally similar discrete states. Our research suggests that SPQ can improve early learning in structured sparse environment while gradually returning to standard tabular learning behavior. However, its advantage is less clear in dense reward or discretized continuous control setting, which remains an important direction for future work. Thank you for listening.